Hi everyone, I'm here. Today we are going to try and make a USB wall charger from absolute scrap. We got this old transformer from an old laptop power adapter that's laying around. We have some copper wire, an old USB cable, some aluminum foil, a diode and a capacitor. Can we use these parts to make a working USB wall charger? Let's find out. First things first. Let's get our transformer. The original device this came from had a 20-volt AC adapter powering it. This means when you plug in a device like this into a wall socket, it will output 20 volts of AC power. This is great for low-power devices, but not so much for something like a phone, which needs 5 volts. We are going to need a way to step down the voltage. This is where our transformer comes in. Transformers can change the voltage of a signal by using the relationship between two coils of wire and some iron. If we put a certain number of turns of wire on the primary side and then a different number of turns on the secondary side, then we can get a different output voltage than what we input. By using some basic geometry, we can determine how many turns we need on each coil to get the voltage we want. To calculate the turns ratio, we take the square root of the ratio of the output voltage squared divided by the input voltage squared, then times that by the number of turns on the primary coil. This gives us the number of turns on the secondary coil needed to get the desired output voltage. In our case, we want to go from 20 volts down to 5 volts, so 5 squared, 20 squared is 0.1 to 25. Take the square root of that and we get 0.35. Multiply that by 100 turns and we get about 35 turns for our secondary coil. Now that we know how many turns we need, we can start winding the transformer. To keep things easy, we're just going to use all of the wire we have and then just adjust the turns ratio accordingly. We started with 100 turns on the primary side and got 35 turns on the secondary side. After we finished winding, we calculated that we actually had 48 turns on the secondary side. This is not too far off from our target of 35 turns. So let's see if we can get 5 volts out of this thing. We hooked up our meter in series with the secondary side of the transformer so that we could measure the current flowing through the transformer. When we plugged it in, we saw a whopping 28 volts, instead of the 5 volts we wanted. It seems like we need more turns on the secondary side to get the voltage down where we want it. Time to rewind. After rewinding the transformer, we got it to the exact number of turns we wanted, 35 turns. Let's see if we can get 5 volts out of this bad boy. We plugged it in and measured a very respectable 5.1 volts. This is getting exciting. Now we just need to add the rest of the circuit and then test it out. To do this, we'll hook the positive side of the transformer to the positive side of the bridge rectifier. This will allow us to get rectified AC that's pulsating at 120 Hz. This is important because we want to use a simple RC filter to smooth out the voltage. We'll also hook the negative side of the transformer to the negative side of the bridge rectifier. Next, we'll hook the output of the bridge rectifier to our RC filter, consisting of our 100 ohm resistor and 100 microfarad capacitor. Finally, we'll hook the other side of the capacitor to the positive terminal of our USB connector. The negative terminal of the USB connector should be grounded, so we'll hook that to the negative side of the transformer. Now we can plug it in and measure a solid 5 volts on our USB port. That's exactly what we're looking for. Now we just need to get a USB cable and plug it in. Oh, and don't forget to add the wall wart. Okay, we've got our wall wart. And now we can plug in our USB cable and measure a solid 5 volts. That's perfect. Now we just need to figure out how much current we can draw from this thing. When we first powered up this prototype, we measured close to 1 amp flowing through the transformer. Now that we've added the RC filter and the USB connector, we only measure around 20 milliamps. This is likely due to the forward voltage drop across the bridge rectifier and the fact that our capacitor is charged and discharged every half cycle of the input AC. This means that the average value of the current is lower than the peak value. Due to this behavior, we decided to add a Schottky diode in series with the USB port. This should allow us to draw more current while reducing the forward voltage drop. With the Schottky diode installed, we were able to draw up to 700 milliamps without the transformer getting hot. We think the reason we weren't able to draw more current is due to the transformer we're using. Even though we have a 1 amp fuse in series with the wall wart, the transformer itself has a current rating of only 300 milliamps. Also, when we tested it, we noticed that the output voltage dropped a little bit under load. This is to be expected because there is some resistance in the transformer itself. And when we draw more current, we get a voltage drop across that resistance. So let's see if we can improve this design. For our next prototype, we made a few changes. First, we replaced the 100 ohm resistor with a 10 ohm resistor. This gave us a slightly higher voltage at idle, but it also allowed us to draw more current. Next, we changed the value of our capacitor from 100 microfarads to 470 microfarads. This reduced the ripple on the output voltage and also increased the maximum current we could draw before the transformer got hot. Finally, we used a different Schottky diode. Instead of using a regular Schottky diode, we decided to use a TVS diode. A TVS diode is basically a modified Schottky diode that can handle more power. These changes allowed us to draw over 1 amp from the USB port, but the transformer still got hot at around 900 milliamps. So it seems like the bottleneck is still the transformer. We did notice that we had less ripple on the output voltage and a higher voltage at idle, which is good. But ultimately, we were limited by the transformer, once again. So it seems like we've reached the limit of what we can do with this transformer. So let's move on to the next one. Our next transformer is rated for 5 volts and 1 amp. Hopefully this will allow us to reach the full 1 amp we're trying to target. We swapped out the old transformer for the new one and made no other changes to the circuit. Let's see how this thing performs. We plugged it in and measured a solid 5 volts on the USB port. Now let's see how much current we can draw from this thing. We cranked up the load until the transformer got hot and measured close to 800 milliamps. Once again, it seems like the bottleneck is the transformer itself. We confirmed this by measuring the resistance of the transformer. We got a value of around 3 ohms, which meant that at 800 milliamps, we would get a voltage drop of around 2.4 volts across the transformer itself, leaving us with around 2.6 volts after the 2-volt drop of the bridge rectifier. This means that if we increase the turns ratio on the secondary side of the transformer, we should be able to get closer to 5 volts. If we look at the datasheet for this transformer, we see that it has a turns ratio of 100 to 1. We can increase the turns ratio on the secondary side by adding more turns. If we take the square root of 1.25 and multiply it by 100, we get about 11.2 turns. This means that we need to add about 11 turns to the secondary side of the transformer to get a turns ratio of 110 to 1. This will allow us to get the output voltage up to about 5 volts. Let's try it out. We added the extra turns to the secondary side and retested the unit. We measured a solid 5 volts and close to 800 milliamps. So it looks like we've hit the limit of this transformer as well. So let's move on to the final prototype. For our last prototype, we decided to scrap the transformer altogether and use a USB IC instead. This IC takes an input of 12 volts and converts it to 5 volts. This means that we can use the same bridge rectifier, RC filter, Schottky diode, and USB connector from previous designs. We also need to add a few small components for the IC to work properly. These components are listed in the datasheet and are fairly standard for this type of IC. We ordered all of the parts from our local electronics store and got to work on the PCB. We designed the board using a free and open source PCB design software. If you haven't tried it, it's really cool. It allows you to make PCBs for absolutely free. All you have to do is sign up for an account and then download the software. Once we finished designing the board, we sent it off to be manufactured. We chose to use a PCB fab for our manufacturing because they have some of the cheapest prices we could find. They also have really quick turnaround times, and their quality is excellent. If you want to learn more about them, check out my video on PCB manufacturing. Once we received the boards, we soldered on all of the components and plugged in our 12-volt power supply. Everything looked good, so we plugged in our USB cable and measured a solid 5 volts. We also built a simple enclosure for the board and added some feet to it so that we could raise it off the table. This way, we could simulate a wall wart. We set the load to 1 amp and let the board run for a few hours. During this time, we monitored the input power and output power using our watt meters. We also measured the output voltage and current using our multimeter. After running for a few hours, we didn't notice any problems. The output voltage and current was stable, and the power levels were what we expected. So it looks like we've successfully made a USB wall charger from scratch. Not only that, but we were even able to make it with a custom PCB. This has been an extremely fun project, and we hope you enjoyed watching it as much as we enjoyed making it. Thanks for watching, and we'll see you next time.